Okay, folks, just following on from the work we did with the data, and if you recall, just to go over that again, as the pressure that's at sea level over here, and that's sea level here, and the pressure drops to practically zero as the higher you go, and by the time we get to 30 kilometers, it's very, very low, and you can see how this graph is falling the way that does. Now, so what we did was, just show it again, what we did was we had a look at what it would be at Everest, at the top of Everest. What would it be at the top of, if we were flying in a commercial jet, for instance, a commercial bombardier flight at 40,000 feet, and what would it be at sea level? Now, what we discovered was from the medical people that the minimum amount of oxygen concentration that's allowed, that's required for you to be able to breathe safely is 19% or thereabouts. And of course we know that 20% of the air is oxygen. So, using PV equals nRT, PV equals nRT, and therefore N equals PV over RT. Using the data that we're able to get, we can easily see that that the number of moles per cubic meter at 29,000 feet would be around 16 moles, 16.41 moles per cubic meter, and therefore the minimum available to breathe is 0.62 moles per cubic meter. That's what's available. So 0.62 moles per cubic meter is all there is available to breathe. Now, if you're in a commercial bombardier flight and you're at 40,000 feet, then the number of moles of all of the air that is available is 10.94 moles per cubic meter. Okay, the minimum amount that you can survive to breathe, again, will come down to 0.42 moles per cubic meter. So Everest, 0.62 moles per cubic meter, and if you're up much further, another 10,000, 11,000 feet, then you're only going to have 0.42 moles per cubic meter. Now, if you happen to be at sea level, of course, this is where we calibrate everything from. So at sea level, the number of moles is 41.6 moles per cubic meter, and of course, the number of moles that therefore you would be able to breathe, that's the minimum that you would need to breathe, is 1.58 moles per cubic meter. Now again, this is based on 20% of air as O2, and the minimum of O2 concentration to breathe is 19%. Now, just so that you can see how that relates to the amount of molecules in the air, 3.7 by 10 to the 23, 2.5 by 10 to the 23 for a flight. You can see that gets much, much less. Okay, and 1.5 times, yes. And then you can see both of these are significantly less than what you need, which is 9.5 by 10 to the 23. So you can see this is why if you are on Mount Everest, and if you're in a commercial flight, even if you could survive the cold in the commercial flight, which by the way, that turned out to be about 220, that was about 220 Kelvin. If you could survive that temperature, then you would only have available to you 0.42 moles per cubic meter to breathe. Now this here, over here, this one over here is has been worked out at 293 Kelvin, which is equal to 20 degrees C. So that's based on that. Okay, so I think if you look at this video and you have a look at the previous one, which describes the pressure gradient, I think it'll be pretty clear to you that why it is that the further we go, the less molecules there are, and it keeps doing that until there are none. And as you can see from the evidence, you can see that that the higher up you go, the less particles there are available, and you can see how many is the minimum amount of particles that you'll need to actually breathe, to actually survive. So that ought to give you an idea about how far you could go up before you would need to have oxygen. So it turns out it's around about 10,000 feet. So and after 10,000 feet, then you'd have a severe lack of oxygen, in which case you'd have to take some oxygen with you. Okay, I think that's pretty clear. The students are now working on the chemical reactions, so we're going to be doing that with them. Okay.